This is a production of Cornell University.
Isomorphic substitution basically follows a number of rules. Okay? The first one is in the tetrahedral, the aluminums are basically substituted for a silica or these other guys right in through here. In the octahedral sheet, iron, magnesium for aluminum or Fe+3. As a result of this isomorphic substitution, it leaves a negative charge. They're unbalanced. If this molecule is now, this crystal is now unbalanced, it basically means, and it's a net negative charge, it basically means all of these positively charged ions that are in the solution from here down, all of these guys, from here to here, these guys can now be sorbed, adsorbed, not absorbed. Adsorbed, they can basically be attracted and held by the clay. Basically, the clay is now a magnet. It's a negatively charged magnet. So anything that's positively charged is going to be attracted to it and held. Does that make sense? Questions? No? And this is what it looks like. Here's my, you can see this little curve here. Here's my tetrahedral sheet. Here's my tetrahedral sheet with an octahedral sheet inside. There's a net negative charge associated with this crystal. Okay? I have edges and I have internal layers. Okay? I have cations basically exchanging on this surface because of that negative charge. Okay? They're going to be attracted to it. And because I have lots of cations in my soil solution, they're going to be in competition for that charge. Right? If you put a magnet on a table and you throw lots of other magnets around here and you start moving that magnet through those other magnets, some of those magnets are going to be attracted to it. Okay? That magnet can only hold so many charges. So if I move this through and I've got lots of little weak magnets being held onto it, and all of a sudden I got a big magnet over here that's really strong, what's going to happen to those weak magnets? They're going to be knocked off and the big magnet is going to come in. Okay? Well, that's basically what we're seeing right here. Okay? We have all of this surface area around this negatively charged cell, clay, okay? And we have all of these positively charged ions out here. They're going to be attracted to it. Okay? This is an introduction to cation exchange capacity. This, all of these ions hanging on top of this is nutrient storage. These are all nutrients. If the clay hangs on to them, they're now storing nutrients for later use. And it all basically spins off of this basic structure. Okay, do we feel comfortable with this? Any questions? I know I zipped through that. All right, well, you guys sure? Because now we're actually going to talk about the variation of that isomorphic substitution and its effect on the clays. All right. We basically have three main groups of silicate clays. We have what we call 1-to-1 silicate sheets, 2-to-1 silicate sheets, and 2-to-1-to-1. And basically it's the arrangement, or perhaps a better way of talking about this is the weathering process, or the results of the weathering process on these clays. The youngest is actually down here at the bottom. This is a chlorite, okay? We're looking at the tetrahedral, and octahedral. In between these tetrahedral sheets, right here, I have another kind of sheet, and this is called a hydroxy sheet. It's usually magnesium dominated. Okay? The magnesium is binding these two sheets together. This is a negatively charged sheet, and that one up there is a negatively charged sheet. So if I have some sort of positive ion in here, it's basically going to act as a bridge, a bridging magnet in essence, and hold the two together. Okay? Now in this case, this is a 1-to-1. This is a 2-to-1-to-1. This is a 2-to-1 right here. The potassium in the middle is basically acting as the bridge. It's positively charged. This is negatively. The one on top is negatively charged. It's bridging them. It's holding them together. Sooner or later, that internal sheet is going to be weathered away, at which point water and other molecules can get in here, okay? Which means that these sheets are basically going to be expansive. When it dries up, these sheets are going to get closer and closer together. When it gets wet, they're going to expand. Okay? Now, depending upon where the isomorphic substitution is, that expansion could be small, and in some cases that expansion could be really large. Now, we have talked about expansive clays already. Remember me talking about vertisoils? Okay, vertisoils are expansive clays. Now, we'll talk about this a little bit later, but depending upon how expansive this clay is, you basically can rip buildings apart. Okay, ultimately this material, we're looking at a weathering product from here to here, from these guys to these guys, from this to this. Ultimately, I'm going to start losing, through weathering processes, these outer sheets. One of these outer sheets are going to go before the other one, and I'm going to result with a 1-to-1 sheet. Okay, and this is that kaolinite. I could have sworn I had one in here. Ah, here it is. I knew I had it in here. Okay, you guys have seen this slide before. Okay, this is the primary minerals. These are the minerals that are coming out of the magma. These are then exposed to the surface. Okay, that mica that I'm passing around at someplace in this room, okay, that mica is basically a primary mineral that starts here. As it starts to weather away, I start losing potassium, and so as a result, the sheet starts separating. If I lose even more potassium, I'm going to potentially go into a vermiculite or a smectite. Okay, here, let's go back. Here's that mica. If I start losing the potassium in the inside, it's going to weather basically straight into these guys. Okay, does that make sense? Depending upon what the weathering is, down here, here's that chlorite. Okay, this is the one that has the magnesium sheet in it. Okay, or the oxide. I said hydroxide. What did I say? What did I call it? A hydroxide sheet. That's this one right here. Okay. If I start losing the magnesium from that hydroxide sheet, this material is going to weather into the vermiculites or the smectites. Cool beans? We understand this, right? Cool. Any questions? All right. How this stuff weathers, there's multiple ways it can weather. It can literally weather from the edge in, or it literally can be taken apart all at the same time. This is a mica at this end, so a lot of series of potassiums in here. Okay? If I'm weathering at my edge, basically I'm unzipping this crystal. Here's the crystal. There's the two tetrahedrals and an octahedral, a tetrahedral and an octahedral. Okay? The edge right here is weathering away, water's getting in here, and potassium is escaping. Okay? And so what's happening is this mica sheet is literally being unzipped. Now if we look at how that potassium releases over time, okay, here's time, here's an increase in release, fairly gradual release, pretty much a straight line, until ultimately you get to the very end and you start running out of potassium. Now you also can weather these guys away by unsandwiching them. You basically literally weather them by releasing them this way. And if that's the case, what's going to happen is I'm going to have a very dramatic release of potassium in the front end. And then I'm basically going to have a flat line. Okay? If you look at this, you can see that I still have one layer intact right here, but the layers on each side have basically been taken apart. Sooner or later, this is either going to unsandwich or it's going to unzip. Okay? By weathering away this illite, just the binding ions that are inside, the potassium, I've basically changed the properties of this colloid. I've changed it from a mica to a vermiculite. Right? Make sense? Literally, by changing that potassium, I've made it into a vermiculite. Okay, so what do illites look like? This is the stick and ball model, and this is the balls themselves. Okay, so basically here you're looking at the electron orbitals, and I'm going to go through a series of these, and they're all going to be basically the same. On this side, you're going to see the orbitals, and on this side, you're just going to see the nucleus with the sticks between them. Okay, so here's my tetrahedral, octahedral. Here's my potassiums, tetrahedral, octahedral. Right? Okay. Because of that potassium in between those tetrahedral, in between the layers, This is what we call a non-expansive clay. It does not expand. The water cannot get into here because the potassium is holding it together. Okay? It holds its dimensions very tightly. Chlorite, fairly similar, but it doesn't have potassium holding it together. It basically has this magnesium hydroxide bond right in here. Okay? When this magnesium hydroxide bond releases, this basically becomes a vermiculite, and it's not returnable. Once this is gone, it's not going to come back. Okay? And basically, both of these, as they weather, basically weather right into this vermiculite. Okay? This is a 2-to-1 mineral. This is a 2-to-1-to-1 mineral. This is a 2-to-1 mineral. 2 tetrahedrals, 1 octahedral. What does it look like? It's an important 2-to-1. It's very similar to smectite, but it has the next one down. I don't know because this is smectite right here. Okay? But it has some very important differences. First of all, most, if not all of its isomorphic substitution is in this tetrahedral sheet, this outside sheet. It's not in the internal sheet. Okay? If that's the case, most of the charge is right up at the surface. Okay, now think about this. If my charge, most of my charge is here, most of my isomorphic substitution is here versus here, what's that going to do to the strength of the magnet? Because these are basically magnets, right? If most of my negative charge is out here versus here, when I throw a positively charged ion into this solution, into this system, what's the difference to that? How is that positively charged ion going to be held by this negatively charged colloid if the charge is here versus here? In what case is it going to be tighter, held tighter? When it's closer to the surface, right? Does that make sense? It's going to hold tighter. If I throw a positively charged ion in here, it's going to be held tighter by this clay if the isomorphic substitution is at the edge versus the middle. Why? Well, think about playing with those magnets. The closer and closer those magnets got to each other, the tighter they held together. Does that make sense? Okay. So if the isomorphic substitution is at the edges, that should tell you something about how this molecule is going to behave. It's going to hold those things tighter. Okay? Magnesium is the usual exchangeable cation that goes into these systems. Okay? And the result of this isomorphic substitution and where that isomorphic substitution results in swelling, a limited swelling to basically 1.4 nanometers. Okay? And because of this charge out here, it has a larger capacity for absorption of those cations than smectites. Okay? Now, if we talked about vermiculites, we certainly should talk about smectites. Because the big difference in smectites versus vermiculites is the isomorphic substitution in the smectites is also in this inner band. It's in this octahedral sheet. Okay? And if that's the case, what does it do to the distribution of the negative charge? It's not all at the edge anymore. It's starting to move towards the inside. Now think about those magnets again. If I have two magnets, one is behaving like a smectite and another is behaving like a vermiculite, which one of those magnets is going to hold on to positively charged ions better? Or I should say tighter. The vermiculite, because the charges are close to the edge, right? It's a better magnet. Okay? Because of that, these guys, these smectites, have a huge swell behavior. Okay, actually, let me go back to this slide. This is my vermiculite. This is my smectite. Because I have isomorphic substitution here, and in this one I just have it here, these clays are much more variable in their expansion. This is one of the reasons why these vertisols are so destructive to foundations. They expand and they contract a dramatic amount compared to the next most expansive clay. Okay? Cool beans? Questions? Go.
A couple slides back, it looked like the chloride and the micas could, whether it's either vermiculite
So the question is, it looks like from this slide that these guys can weather basically into this or this. And that is true. They can. It depends on what the weathering environment is like. Okay? And if we have a different type of, a more intense weathering environment with more isomorphic substitution, I'm directly going to be getting into that octahedral sheet. I'm definitely going to go straight to the smectites. Okay? If it's a less intense weathering environment, the first things that are going to get weathered, and I'm going to see isomorphic substitution, is the outsides. Okay? Once I start unzipping these things, they're basically, both of these are basically vermiculites. The only thing that's different between these and vermiculite is the binding layer between them. Okay, so this one has a magnesium hydroxide sheet. This one has potassium. If I get rid of that, this is what I got. So for me to be moving to this environment, I have to have a much more intense weathering environment. Or for me to move to this type of clay, I have to have a much more intense weathering environment. Does that make sense to everybody? Questions so far? Okay, so the smectites. All right, let's go to the last one. We went from smectites. Let's actually go to kaolinites. And if we talk about kaolinite, let's go back to this very first slide that I showed you earlier on. This is a kaolinite. This is a smectite. It now makes sense why these guys are a lot larger than these guys, doesn't it? Does it make sense to you guys? Now let me ask you a question. Why are these this shape, though, versus these guys? What is it about the smectites? What's happened with smectites? Go. They have edge weathered, and edge weathering is part of it. They haven't completely weathered, though. Okay, if we're looking at this sequence, if we look at this sequence, we're basically looking at a weathering sequence. When we get down to here, we're a really weathered environment. Okay, as we move from here to here, we were also going through isomorphic substitution. And if I start thinking about isomorphic substitution, I got to think about two things, or three things. First, where the isomorphic substitution has occurred. Basically, the difference between this and this. Okay, this one's on the edge, on the tetrahedral. This is in the tetrahedral and the octahedral. All right, this is more expansive as a result. Okay, so I have to figure out where it is, but I also have to think about what's doing the isomorphic substitution. And you remember us talking about this? It's not just about the charge change. It's also about the size of the ion that's moving in. If I start pushing in, if we go back to this slide, if I start isomorphic substitution by pushing in things that are larger than the radius that could generally fit into that space, what am I going to be doing to the shape of my crystal? Let's go to a flat one. Where's the flat one? Do I have a balloon chart of a flat one? Maybe not. I don't. Sorry. Let's use this one. If I start pushing in ions, imagine here, this one right here. Okay, this is a silica. If I start throwing an aluminum in there, for whatever reason, let's pick one that's larger. Okay, I throw an aluminum in there. What's going to happen to the shape of this crystal? I literally have a bigger balloon in there. What's going to happen to the shape of this crystal? Is it going to be flat anymore? No, it's going to have a bump in it, right? So I'm going to start changing the shapes of these colloids. Okay, and if we go back down to this last slide, somewhere in here. Yeesh. Here it is. Kaolinite versus smectite. Obviously bigger. These are smaller. These are also nice and flat. What do I see there? What do I see? I see ridges, I see curves. Basically, the isomorphic substitution that's gone into these sheets have morphed the shape. It's still a crystal, but the shape of the crystal is no longer flat. What's that going to do to the behavior of this volume? What? It's going to change the size of the pore. It's going to change the nature of the pores. Okay, this stuff, this smectite, it's expansive. So when it gets wet, it's going to start expanding. Okay, but it's got strange shapes. So it's not going to necessarily expand exactly like this. It's going to expand like this and like this and like this. Okay, all because of the nature of that crystal. Okay, questions? Does this make sense? Because it's this isomorphic substitution and this sequence of these colloids that are going to be driving the next unit. We're going to talk about pH, we're going to be talking about CEC, we're going to be talking about organic matter. It's the nature of these colloids. Okay, questions?
This has been a production of Cornell University, on the web at cornell.edu.